So now we're going to move on to aqueous stoichiometry, and this isn't really any different from regular stoichiometry, which we already know, except that now we're going to be dealing with things given to us as molarity. So it says when barium nitrate and potassium chromate react in an aqueous solution, the yellow solid barium chromate is formed. Calculate the mass of the barium chromate that forms when 3.5 times 10 to the minus third mole of solid barium nitrate is dissolved in 265 milliliters of 0.01 molar potassium chromate solution. Again, it's one of these problems where there's a lot of things given, but once we organize it, it's not too hard. I'm going to click to the next slide, which still has the problem here at the top. And the first thing I'd like you to do is to go ahead and write the balanced equation for the reaction. Use it as a self-test, and I want you to pause the video and make sure that you can write this reaction. Okay, check your work. Is this what you got? Did you get barium nitrate plus potassium chromate equals barium chromate plus 2 potassium nitrates? If you did, then that's good. It told us that these two are aqueous, so here's where these precipitation rules come back into effect. And then it already told us that this was the solid, but we know that potassium nitrate is definitely aqueous, both because of potassium and the nitrate. So let's go through and take out our information. Calculate the mass of barium chromate, question mark, grams, that forms when 3.50 times 10 to the minus third mole of solid barium nitrate is dissolved in 265 milliliters of 0.01 molar potassium chromate solution. Now I'm done with my problem. I don't need this information up here anymore. Anytime I'm given two reactants, what type of problem is it? It's a limiting reactant problem. And so this is one of our harder stoichiometry problems, but I figured I'll go ahead and introduce the harder ones because just doing regular aqueous stoichiometry then will seem pretty simple. So I'm going to start with the barium nitrate because that's already given to me as moles, and I need to see, okay, how much, if I have barium nitrate, how much barium chromate can I form? So that problem involves 3.50 times 10 to the minus third moles of BaNO3 2. I want to get rid of moles, so I'm going to put my moles of BaNO3 2, and I'm going to convert to moles of BaCrO4. It's a 1-to-1 ratio. I want to get rid of moles of BaCrO4, and I want to convert it to grams of BaCrO4. I have 1 mole, and my molar mass is 253.37 grams. I go ahead, I put that into my calculator, and I end up with 0.887 grams of BaCrO4. Okay, that's great. But let's look and see if that's the limiting reactant, because now I need to take a look at this reaction and see how much is produced when I do that. So that's given to me as a molarity, and so I need to solve for moles. So I know that molarity is equal to moles over liters, and I know that my molarity is 0.0100 molar, and it's equal to X moles over, and this has to be liters, so 0.265 liters, because 265 milliliters isn't good. I'm going to go ahead and multiply those two, and I'm going to get 0.00265 moles. Let's go ahead and do that problem. 0.00265 moles of K2CrO4. I want to get rid of moles of K2CrO4 and convert to moles of BaCrO4. Again, it's a 1-to-1 ratio. I'm going to put moles of BaCrO4 on the bottom, grams of BaCrO4 on top. My mass is still 253.37. I calculate it all out, and I get 0.671 grams of BaCrO4. That means I'll get myself a new color here. Let's go with purple. That means that this is the least amount produced. So this is my answer, and therefore it comes back to tell me that this is what limits my reaction. If we were just given this information here and not given the information with barium nitrate, we would just simply solve for the moles and then go through and do the stoichiometry. But I wanted to give you the hardest type of problem, a limiting reactant problem, as our sample one, so you could see all the steps that were involved.